So now that we've covered inverse functions and how to find inverse functions and dealing with them, it's time to kind of move into the calculus of inverse functions. And so the natural thing you might want to do is deal with the derivative. You could say, well, why don't we deal with limits? Well, we could, but if you find an inverse function, the limits for inverse functions are pretty much the same as for any functions. But the derivative of an inverse function has a very interesting relationship to the original function itself. So let's set up some preliminaries. The first thing is that let's just assume that we have an inverse function, that it exists. And if we make that assumption, or we verified that somehow, let's go over some things that we technically already know. The first is that, by definition, if a function has an inverse, then running the inverse of the function through the regular function should get you back to where you started, right? You go there and you just come back. And this will come into play later. The second one is that the derivative of x is 1. I hope that we all know this. The next thing is the chain rule. And in the chain rule, when you take the derivative of f of g, you get f prime, and you plug in g, and then you multiply by the derivative of g, or g prime, however you want to write it. And then the final thing is related to inverse functions. If f of c equals a, then f inverse of a equals c, right? They have that relationship that you can run it through that way. So we're going to use all of these pieces over here, and we're going to kind of do a mini proof of how do we get there, and then we're going to use that result as we do examples. So how would we find the derivative of f inverse at x equals a? Or there's another way to write this, and it's this f inverse in parentheses prime at a. I don't like this notation because there's too many parentheses for me. I know this is actually like more writing, but to me this is very explicit. It's the derivative at a point versus, I don't know, something about that prime with parentheses, I just don't like it. So that's just personal preference. If you like this, feel free. And given that we know that f of c equals a, right, we're just really leveraging this. So there's a little bit of a trick here that we haven't talked about, and we'll get to at the very end. So the first thing we do is we use this fact. We say, okay, well this is a relationship that exists. So if we take the derivative of both sides, we can use the second fact and get this. So this derivative of this piece. Then what we do is we say, oh, I have a composition of functions. I can use part 3. So that tells me that what I do is I take f prime at g, which in this case is f inverse, times the derivative of g. So that's, okay, so all that's equal to 1. But if you think about it, what am I trying to find? I'm trying to find this derivative here. So I can isolate this derivative by itself by simply dividing out this piece. I can just take this and divide it over here, and I can say, okay, so the derivative of the inverse function is 1 over the derivative of the original function, but instead of plugging in x, you plug in the inverse function. So if you wanted to find this explicitly, if you wanted to say, well, I don't want some complicated formula, I just want something in terms of x, what you'd have to do is you'd have to still find the inverse function. And then you'd have to find the derivative of the original function, you'd have to find the inverse function, and then plug it in for x. But if you do that, you can simplify this, and now you just have the derivative of the inverse function. So you really don't have to take the derivative of the inverse function, because sometimes the inverse function itself is just nasty. Like what we're going to find is things like arc sine, the inverse sine function. What would that even mean to take its derivative directly? We don't know, but we can use something like this to figure out what the derivative of arc sine actually is, or the inverse sine function, same thing. We can leverage that we know very clearly what the derivative of the sine function is. So anyway, I say all that, but to do this you have one issue, and that's you have to find f inverse, and that's not always easy to do, so you have to be more clever about it. But if you're just trying to find it at a single point, because if they say, okay, find the derivative of f inverse at, let's just say x equals 1. what you do is you find a value if you plug it into the original function that gives you 1. So let's say that that value was 10. F of 10 equals 1. So since you know that, instead of using this piece, you can just say f prime at 10, because that's the value that is related to f inverse of 1. So yeah, it's a little tricky. We're going to write down some ways to do that and give some steps, but this is the preliminary example, or this is the theory behind what it is, and we're going to compute some practical examples to try kind of give you that grounding in explicit functions.